Hello, everyone. Welcome to this new edition of the APEC IUC 2020 Groundbreakers APEC Virtual Tour. I would like to invite you to take a look in all the sessions that we have for the next couple weeks. We have a lot of content, some workshops, hands-on labs, tracks on English, Japanese, Chinese, and Korean. And I want to say thank you to all the user groups, including the Java user groups from the region for supporting this event, and also to our sponsors, Oracle Groundbreakers and CloudDB. Today we are here for a session, How to Develop Graph Database Applications by Gautam Pisharam. And I will recommend you to take a look on his session with more details afterwards, as the recording of the session, the playback will be available for a period of time of 2 weeks. Also, in the page with the recording in the Hey Submit system, you will be able to place your questions, comments, suggestions, and Gautam will be able to interact with you and answer all your questions. Please feel free to add your input to this session. And without saying more, I will leave you now with this excellent session about how to develop graph database applications with Gautam Pisharam. Thank you so much, and please enjoy your events.
Greetings, everyone. Welcome to the session on how to develop graph database applications. Myself, Gautam Pisharam. I'm a cloud specialist, part of Technology Engineering Hub within Oracle. I would also like to acknowledge Ryota Yamanaka, who is a product manager for Oracle Graph for JAPAC region. Ryota Yamanaka also runs a great GitHub repository with nice assets on Oracle Property Graph. I would also like to encourage everyone to access Ryota Yamanaka's GitHub repository for more contents on Oracle Property Graph. Today's session is mostly focusing on graph-based database applications, an Oracle offering on the graph analytics. We'll see various examples on how we can leverage graph as a product based on the relational data in the database. This is our mission statement. It's to help or enable people see different ways to see the data, discover the insights, and unlock the endless possibilities. As we can see, Oracle Graph is one of the product offerings under the analytics umbrella, which helps people see the various hidden patterns or the connections between the data points. So like Oracle Graph, we also have Oracle Spatial for geographical insights. We have Oracle Analytics Cloud for advanced visualizations and advanced analytics like clustering or the forecasting. We also have multi-dimensional offerings like Oracle S-Base, which is mostly used in the multi-dimensional space. We have the data science in the Oracle Cloud Infrastructure, big data stack, a lot of product offerings. So we enable people to see data in new ways. And in this session, we'll be focusing more on the Oracle Graph, and within Oracle Graph, we'll be focusing on Oracle Property Graph. Let's take an example of what exactly is a property graph. So before getting into property graph, within graph or within Oracle Graph, we have two types of offerings. One is the property graph and one is the RDF graph. And this session is mostly focusing on property graph. We are not covering the RDF graph. Let's see property graph with an example. As we can see on the screen, it's a screenshot or a visual representation of different transactions between different accounts with details on who has transferred it, who is the owner of a particular account, which company that person works for, and the associated attributes related to the transaction. So if we try to start from the right hand side of this particular screenshot, we can see that Liam who is the owner of account 2090, has transferred a money of close to $10,000 to account 10039 to the top left. And from that particular account, we can see a transaction of close to $1,000 to the account 8021, who is owned by the person Nikita, which we can see on the bottom left of the screen. We can also see that there are two transactions being transferred between the accounts 8021 and 1001, different accounts and different transaction numbers. And finally, we can see that there is an amount close to $10,000 going back to the original account 2090. And in between, we can also see that Camille is the owner of 10039, who in turn got that initial transfer of money from 2090. And we can see the association because Camille works for Oracle. And we can also see that that particular business entity is the owner of that account 1001. Now, in a good world, this all works fine. Um, Various banking institutions leverage machine learning modules to understand the pattern in which the money is being transferred between different people. And then they base these insights on the transactions to come up with recommendations. Let's say, for example, just because of the lot of transactions involved in this particular screenshot, they'll be able to generate recommendations between the different people who are involved with the transactions. It could be an offer based on the credit card. It could be an offer based on their previous purchase history. Based on the insights that we generate from the behavioral patterns of the financial transactions, we'll be able to generate recommendations or make machine learning offers, which kinds of build trust between the customers as well as the banking institutions. When we take an example of a financial transaction cycle, uh, we know customer comes first for the financial institutions, but then these days we also know that customers depend a lot on the financial institutions as well. They want to leverage the maximum services. The technology is so advanced that you basically use a mobile app or a web app to trigger any kind of a transaction involved in your day-to-day life, or a banking app to take care of any of the life needs. Now, let's see more examples on how a graph can be leveraged and how a graph can be helpful to the business analysts or the data science teams to uncover the hidden insights or the patterns within these financial transactions. Let's look into some more attributes of the property graph with this particular example. So we can see that there is a name of the graph, financial transactions, and name of the graph is something which we usually define when we define a property graph within Oracle Graph as a product. The different elements of Oracle property graph, it will always have a vertex or a set of vertices. In this example, where we have highlighted, account number 2090 is the vertex of that particular account. We also have different vertices. So account is one of the vertex. Like that, person is a different vertex. Company is a different vertex. So they are all part of the vertices. So every vertex comes with its own labels and its own properties. Now we have the edge, which is basically the connection or the relation or the transaction between the two different vertices. In this case, we can see that Liam has owned that account 2090. So owner of becomes the edge and the relation between that particular account and the person. Label of the vertex, obviously person. In case of company, company is the label of vertex, which is coming with the name Oracle. Or account, the label of the vertex will be 2090 or 1001 or an 8021 or a 10039. We also have label for the edge, just like we had owner of between the relation account and person. Between two different accounts, we also have the edge transaction with its properties like the amount, the actual amount that's being transferred between the two different accounts. So we have the property of vertex as well as the property of the edge. So edge is a transaction, and like we highlighted, amount that is transferred between two different accounts becomes the property of the edge. So in a nutshell, we have different vertices, different edges, different labels for edges, different labels for the vertices as well. So typically, if you look now, we look into the bottom right. This is how it is traditionally defined within uh, a relational database, wherein we'll have different uh, tables. There will be a separate table for all the persons or the individuals, and then we'll have a detailed table for their account information. We'll have a different view, maybe connecting the accounts and the persons. We'll have a different table for the companies. We'll have a different table for the transactions. So individually, we'll be storing multiple detailed transactional tables within a product like a database. And then they will all be connected with foreign keys as well as the primary keys. Uh, what Oracle database then does is it has this built-in graph capabilities, wherein as we highlighted on the top left of the screen, we'll be able to generate the relation between different attributes like the customers, their accounts, their companies, and their transaction details by leveraging Oracle Graph as a product. We'll be getting into more detailed as well. So just wanted to highlight that, like we have in the bottom right of the screen, that's how traditionally the accounts and the various detailed transactions looks like in a traditional database. And in an Oracle graph, as we can see on the top left, that's how we'll try to translate it into the product so that we'll get to know in a visual way the relation between the different people, the different organizations, and the pattern in which various transactions taking place. We'll come to examples on how a pattern looks like, or what are the different types of patterns that we usually deal with. All right. Getting into one more example. So in the last slide, we were looking at a bit more complex, or I would say there are like multiple tables involved in framing a graph query. Let's look at a very simple example. We have an accounts table that comes with its accounts ID, and then we have the transactions table. The transaction tables has the from account and the to account. So basically, uh, the source account and the target account, and then we have the amount transferred between the two different accounts. So we have two tables, and then let's see how an Oracle database can enable you to frame a query or a PGQL statement, which can then convert the traditional relational database information into graph. We can write a query like this. So it says create property graph bank underscore graph, and my vertices are going to be the different accounts, and my edges are going to be the various transactions. And I'm also basing it on the from account to the two accounts. I'm basically giving it a source key and the destination key based on which it will be able to generate the graph. And then I also assign the different labels both for the vertex as well as the edges. And this is something which we'll define within the Oracle database stack to generate the graph from the graph database. We look into the architecture options in more details now. So one option is the two-tier approach, wherein the queries are run within the database, and then you use a client to load the data from the database into the graph set. So what happens in an Oracle database is that you have your traditional or the relational tables, the schemas, the various views that you hold, from which you'll be able to generate the vertex table and the edge table. It's something that we traditionally refer as graph schema. So graph schema is part of the graph database. It is built in with the Oracle database, about 12.2 version, and even in the cloud offerings. So you'll be able to write PGQL queries, just like how you write a SQL query against a traditional database. You'll be able to write a PGQL query against the graph schema, and then be able to generate the output from the shell command. If you want to take it to an advanced level, you need to deploy the graph server as well. It's a component that you get to download separately, uh, where you can leverage the graph server to load the data from your graph schema. When I say graph schema, the vertex table and the edge table, and then load it to the in-memory. So the command that we saw in the earlier screen, it was basically generating the vertex table and the edge tables for you, which will basically convert your traditional information from the relational database. That particular graph schema can then be loaded into the in-memory, wherein you can run advanced analytics on top of it, like the various built-in algorithms, which we'll get to it once we um, get to the use case stages of this particular session. That's the two-tier approach, wherein you have the graph database. You can run queries on top of it, or you can load it to the in-memory option. The second is the three-tier approach, wherein you have your database tables ready, and there is a mechanism in which you can directly load the information from your relational data into the graph server directly without even having to convert to your vertex table and the edge table. So just by maintaining a relational database, you can quickly use a configuration file to load the data into the in-memory, and it gets converted into the graph equivalent format in a near runtime process. Um, both um, both approaches are used by various organizations. Say, for example, if you want to look at a long-term approach wherein you want to load incremental data in a very structured way, such a requirement can be addressed by having a vertex table and an edge table within the graph schema. So basically maintain the data in a graph format in a very handy way so that it can be referred even by running queries within the database. Now, for data science teams, wherein they want to quickly load the newly generated relational data into the in-memory, they can go for the second approach we discussed with the three-tier, wherein they can have a configuration file and they can directly load it into the in-memory. Having seen some details around how a graph looks like and how it is different from a relational database, let's now get into the core of Oracle Graph, which is basically the various patterns that we can detect using the various queries. So what are the different types of patterns that we usually see with Oracle Graph? The first one is called as cycles. Cycles are heavily leveraged in financial institutions, mainly to generate the behavioral interest on different customers on how they are transacting the money between different accounts, how they can learn from the behavioral patterns of different customers, and how they can offer insights so that the customers can be retained. Cycles will be very helpful in detecting the good part of financial transaction as well as the bad side of financial transaction. The goodness is that by understanding the behavioral patterns, the financial institutions will be then able to generate recommendations or make offers based on the machine learning modules that really learn from the behavioral patterns. On the bad side, the similar kind of a financial transaction. So let's say, for example, if certain people opens an account and then they keep transferring money between different accounts, and they'll be eligible for different offers, they can in turn take advantage of the machine learning module. They can do various transactions between different accounts, the same amount being transferred between different accounts, and can leverage various offers for the recommendations and can just manage without a trace. So it can be either used in a good way or a bad way, which is in turn the advantage of Oracle Graph. You'll be able to really judge the behavioral patterns between different connections of different nodes or the customers. As we can see on the screen, cycles are basically a closed loop. So let's say, for example, if I'm a person A and I'm transferring money to person B, person B transferring money to person C, and that person C in turn transfer it back to person A, which is myself. That completes the loop. That's called a cycle, and financial institutions try to leverage a lot of insights based on cycles because they will have multi-million or multi-billion transactions, and it would be very beneficial to look into the cycles as well, especially in detecting the financial fraud. That's again one of the advantages of Oracle Graph. Um, um, some use case like a financial fraud detection. It is very essential, or the first step of identifying the financial fraud is not identifying the fraud itself, but trying to identify how many cycles you have. And it takes a bit of a scalability and questionable performance levels to really get into that multi-billion financial transaction cycles and being able to fetch the cycles for you in real time. So that's one of the patterns. The next pattern is ranking. As we can see on the screen, it's a very peculiar money flow wherein you can see that the dot in the middle of that particular money flow section is generating a lot of interest. That particular account is getting money from different customers, and then it is just going to one particular account. So you can basically use it for any suspicious activities as well. It could be treated like a suspicious pattern. The below screenshot, as we can see, a single account getting money from multiple directions. It's also ranking. You can basically run your page rank, and you can identify the closeness between one customer and different customers, and then being able to find the insights from it. We'll see with an example how we can leverage these algorithms in an example like a product recommendation. So as we can see, we can also try to identify like the suspicious accounts belonging to different fraudsters. Can it really predict where that particular node is a fraud, and if he or she can be influential to different accounts? So a closeness or attaching weight to customers will really give insights based on that. Other than cycles and ranking, we also have paths. So it's a grid layout that we have here. Paths can be very much beneficial. Let's take an example of a public sector, of a water network. In a city, there will be a lot of water networks. And let's say, for example, there are multiple water networks connecting between the regions. And say, for example, between two regions, one of the water network pipeline is broken. How to find the shortest path? So that you can get alternate water supply from a different pipeline, which is fed from a different reservoir altogether, and to make sure there is very minimal water loss in the pipeline that initially got affected. So how to maintain the efficiency of the water flow? It can also be addressed in a different case, wherein, let's say, for example, you have a particular area which is getting developed in a very fast rate than anticipated. Now, how can you make sure the adequacy is met? Whether trying to identify whether the existing pipelines are adequate enough to feed the different increase in population that we have in a certain area. The same concept can be used in a road network or a electrical network, wherein you can identify if there is a problem with one of my road network, how to make sure the inflow of the traffic or the outflow of the traffic is not affected by having a different alternate route connecting to that particular route. Same with the electrical um, network as well, how to make sure the electricity is not impacted by having supply from different areas. So paths can be really efficient in addressing some of these um, public sector use cases. It can obviously be used in the financial fraud circle as well, based on the hope analysis to find how many hopes in a shortest path you have between two different nodes, or find accounts through which most of the money flow. So path analysis can be useful in that particular way. And obviously you can also have the complex pattern. So we have one of the complex pattern, which is highlighted on the top right of the screen. And now just take an example. We identify that now 4 of these nodes which are highlighted in the circles have many multiple connections between different customers in the screenshot. And we also identify that there is a direct connection between the 259 and the 387 IDs. Now, this can be then used for further insights, trying to identify whether it's a suspicious account. Can we predict whether it's a suspicious account belonging to a fraudster, or whether can we equate this to be part of a community? Whether those two nodes can influence a different community being a fraudster. So we can get insights like this from the behavioral patterns of the customers. Now, how do we really get this information from the Oracle graphs? We have to write PGQL queries. So PGQL stands for the Programmable Graph Query Language. It's very much similar to SQL. So let's say on the screen we are seeing select V from graph match V. It stands for, so it basically fetches the different vertices that I have in my graph. Then we have select E from graph and match a pattern. So we are basically matching a pattern there. It's basically fetching all the edges wherein some attribute is there between the vertices. So it basically fetches information from my graph database, from my in-memory graph server on all the information that has happened. Let's take an example. If it's a financial transaction, then it basically fetches all the transaction between all the people. So it's like a select star query. We can also notice that the difference between the second screenshot and the third screenshot is that you have an arrow missing, which means that the second one is mainly for a non-directed graph. So it basically gives you all the graph details irrespective of the direction. Whereas the third one gives you the result wherein there is a direction. So if I want information very specifically regarding the transfer from one account to a different account, and if money is not being transferred from the other account back to this account, it gives only that first account information, wherein the second query gives me everything. You can also have filters. You can find transaction based on your names or the different attributes of your graph. You can match your vertices and then say order by. You can also have conditions like give me the list of transactions where the amount transferred is more than an NX amount, or give me the list of vertices as well as that. So the difference between the last two queries, one is selecting just the information related to the edges, wherein the last one is also taking the actual names as well as the detailed edges. You can also have it like a you can also match it like a pattern, like who has transferred. So you can basically say, give me the list of transactions which matches one of the properties. The last one, again, it's a pattern matching, but then let's take, for example, in case of financial transaction, it could be possible that the individual customers can transfer the money. It will be like a person-to-person transfer. But then if you want to generate a graph query based on company-to-company transfer. So in a financial institution, it's possible that companies will transfer money to companies, person will transfer money to companies, person will transfer money to persons. So if you are interested in fetching graph query based on just persons or person to person, person to company, company to person, you can specify that as well. So it's a very easy way of trying to get the information from the in-memory applications. So the PGQL commands can be written in multiple ways. You can leverage the graph visualization GUI to write the PGQL queries. You can also write the PGQL queries in the graph shell, and you can also leverage the Zeppelin notebook as well, right? The graph query language. It will directly fetch it from the in-memory graph. Let's quickly get into the first demo. Let's start with a very basic example. So if you recollect, we were trying to look into an example in the very initial part of this session, where we are looking at a set of friends transferring money to different people. So let's say, for example, we want to understand the overview of account holders that have transacted with a person named Alice Nguyen. You can basically write a query, which is a PGQL query, which basically takes the information on all the transactions related to Alice. So I've written that query, and this is how the graph is generated. We can see that Alice owns this particular account, and from that particular account, there are multiple transfers to different accounts. And then the individual accounts related to that particular account also have transfer from different accounts. You have transfer related information. You also have the withdrawal related information. So you can have multiple properties associated to different vertices. Let's try to change this from the name to IDs. So if you want to look at it in a different way, wherein you need to get information on from which account it has been transferred to different accounts. So 201 is the customer ID, and then it owns this particular account from where money has been transferred from 101 to 102. Now 101 is a customer ID who owns the account ID 102, and then there is also a withdrawal from a different vertex as well. So this says ATM. So basically says from this account there is a withdrawal from this particular ATM. And if you right click on here, you can see that it's a account. So this particular account, and then you have the account information mentioned here as well. So this is a very basic example of how Oracle Graph visualizes the graph for you in the visualization GUI. Let's try to get into more details now. All right, so let's take an example of the financial cycles. We have this graph called as cycles loaded to the in-memory. So I'm writing a PGQL query here. So this PGQL query basically says, it basically lists the number of transactions between different people, limiting by the 10. So it basically fetches the first 10 transactions from the in-memory database. Basically says that from account ID 1, there is a transfer to 584, 644, 259, 489, 672. So 5 transactions here, and then from account number 2, another 5 transactions, basically transferred to different people. Let's try to look into more details. So first, we'll try to identify a 3-node cycle. So when I mentioned 3-node cycle, person A transferring money to person B transferring money to person C, connected by edges E1, E2, and E3. Again, limiting by the 10 transaction. So in a nutshell, we want to identify a 3-node cycle wherein there is money transfer between person A to person B to person C, and then person C transferring it back to person A. And then we try to limit it by 10 transactions. Now you can see that it has basically taken 10 of those transactions. If you just take an example here, we can see that 134 has transferred the money to 22, and 22 there is a transfer to 101, and then 101 has transferred it back to 134. You can also try to change the different properties here. Right now I have selected it as ID. You can also select different information here. So let's say, for example, I just want to give my ID here and my label here. So it basically changes it back in a different way. I'll put back to ID and label. So this is basically a 3-node cycle, limiting it by 10 cycles. Now let's remove the limit and see how many 3-node cycle we have in this particular in-memory. You can also see that it has listed only one page of cycles because we were very specific in selecting the first 10 cycles from the in memory. Now let's see how many cycles we get in this graph. So there are many multiple cycles being transferred between different accounts. So let's take, for example, I'm just trying to drag this. You can see that there are many 3-node cycle associated with this particular ID 359. So it could be it could be treated like a hidden pattern, trying to find the closeness between different people. So 359 is closely connected to different edges, wherein there is a lot of money transfer has happened. Let's try to get into more queries. Till now, we were interested in looking at a pattern to identify the cycles. Let's see how we can run the top to shortest path. So when I run this particular query, I basically get it in a table format. I'm mentioning to the system to retrieve me the top to shortest path from the list of transactions that has happened. And we can see that there are in fact 2 6-hop cycles, starting from 259 ID to ID 1, and then from 0 to 3430. Now, let's try to write a query wherein you want to see the actual information connecting this particular shortest path, which starts from 259 and to the ID 1. So I can write a query like that. Since I know that it's a 6-hop cycle, I am explicitly writing I want information on all the person and all the edges. So now we can see that there are many transactions, the 6 cycles, basically. The 6 cycles, starting from that 259, you can see that it has gone to 387, it has gone to 38, and then it has come to 687, and then it has gone to 1, and then it has come back to 259 itself. So that was one more example of the query. Let's now try to identify many multiple cycles. Now we can see that for that particular ID 259, there is in fact many multiple cycles. We just tried fetching the shortest path connecting that particular ID 259, but then we can also see that a hidden pattern that 259 is in fact involved in many multiple cycles as well, other than the 6-hop that we selected. Now let's say I want information on all the 6 hops from the list of transactions. I can run a PGPL query for that. So we can in turn see that the graph visualization GUI has given me the list of all 6 hop. When I say 6 hop, there is a transaction happening between different 6 customers. So there are different ways to visualize this information as well. This is a force layout, as we can see here, which can be zoomed in as well. But if you want to visualize it in a different way to make things easy for your eyes, you can also go for a, let's try to select a grid visualization here. In a grid visualization, you can easily try to identify the connection between the different 6 nodes in a different way. So it gives an easy way of identifying this. So this was an example of leverage the programmable graph language to write queries. Now let's take a quick look into the various algorithms that can be leveraged. Let's say first we have the screenshot, and how you would typically identify patterns from this. We have different algorithms like the PageRank, betweenness, which are all part of the centrality matrix. Centrality matrix is basically trying to identify the important edges connected to a node. So PageRank, as we can see in the top, the bottom left of the screen, it basically tries to identify the important connected to a node. Then you have betweenness, which helps you explore and discover the uh, communities. So communities which like you can see on the bottom right, the communities can be really helpful in identifying the influencers. If there is an individual connecting different communities, who is then influenced for fraud patterns or even for the good patterns. On the top right, we have the path analysis. Basically, we called it as hope analysis to find how many hopes in a shortest path we have. It can be used in a financial to find accounts through which most of the money flow. It can be used in a product recommendation related retail. It can be used in a law enforcement related use case wherein vertices with high between centrality values will determine the link between different groups. A path analysis can be also leveraged in telecommunication or analytics, wherein we already discussed a use case related to the water networks or the road networks. To leverage graph analytics, we have to make sure we have the graph server deployed on top of the property graph database. Uh, and how you will leverage it? You will basically load the information from the graph database into the graph server to the in-memory, and then you run the algorithm on top of it. Let's see on how recommendation works. So whenever it comes to a use case like recommendation, the first step will be to define the graph model. Let's say you have different customers and you want to offer different products against those customers. So it's very easy to analyze. We need the customer dimension, the product dimension, and the various attributes like who has purchased what or what was purchased by whom, through which you will be able to offer the recommendation. So first is to come with that graph model. Then you understand the source structure. So you will basically have the customer tables, you will have the product table and the sales related table, which is the actual transaction information, who has purchased what or what has been purchased by whom, the actual amount, the detailed transactional information. So you basically try to understand what the organization has deployed it. Based on the details, you then create the mappings by identifying the vertex table. In this case, vertex tables are the customers and the products. And then you have the edge table, which is basically fetched from the sales table, wherein the source will be the customers and the destination will be product. So a customer has purchased a product. So customer is the source and product is the destination with its labels with the sales related details. And then you try to apply algorithms on top of it and then try to improve the models. So let's take an example of personalized page rank, which can be run on top of it. So a page rank based on the, how do I say, page rank basically works based on the ranking on the various nodes. So let's say, for example, you have customers and products. The higher the page rank for product, the higher the possibility of that particular product being recommended to a customer. And how that page rank works. So if a product has a high page rank that is shown to a different customer, the reason could be that that particular customer is connected to multiple customers, and those multiple customers would have purchased this particular product. So based on the closeness between one customer and different customers who has purchased a product, that particular product will be having a high page rank, and that will be offered as a recommendation to this particular customer who is the target customer. We also have the deep walk or the random walk algorithms. So basically, it's trying to find the similarity between different customers and the products. Let's say, for example, a set of customers has purchased a set of products. So we can look into the behavioral patterns and then throw a recommendation on the similarity or the taste levels on product purchased by similar customers are recommended for a particular target customer who share the same interest. We also have the collaborative filtering, wherein you can use algorithms like matrix factorization. So it's basically trying to predict the affinity between customers and the products, through which you can identify the same taste between customers and the products, and then throw the possibility of purchase of a particular product with a particular customer. Let's get into a quick demo of it. So already run this demo here. Let's look into this in detail. So this is the shell that we have, and initially we are trying to read it from a config file. So the shell basically try to leverage a config file, and let's also look at the config file now. So the config file is trying to connect to a database, and from the database, it then tries to refer different tables within the RDBMS. And I have mentioned all my vertices information and my edges information here, the various product, the properties involved with vertices and edges, and based on which we'll be able to fetch the graph data from the database and then load it into the memory. So this particular step I'm highlighting here is basically fetching the data from the Oracle database and then loading it into in memory, and then I can write my different statements. So let's say, for example, I want to write a very simple statement to get the list of products by limiting it to 3. So it's basically fetching 3 products from the set of retail information that I have from the um, uh, graph data that is loaded to the in memory. And now let's say I want to get the list of the products purchased by a customer. With a customer number 12353. So I'm interested in getting the list of list of products purchased by this particular customer, and I can have a query written like this. It basically gives me the products purchased. And then what I can do, I can then try to run a personalized page rank for this particular customer. So let's say I'm running a page rank for this particular customer here using this particular command, and then I run the personalized page rank using the shell, and then basically get the top 10 recommendation for that particular customer. So the system has actually given me back the various recommendation. Now, how this can be visualized in the graph GUI? So I can go back to my visualization, and let me just say it like this. So all the products that I have here, I've written a PGQL query, which was basically the result set by applying the analytics algorithm in the background. It has given me the top 10 products. And now I'm trying to identify the closeness between this particular customer. Why those products were offered to me as part of a recommendation by trying to reveal the information on the other customers. So here I can see that this is my customer 12353, and then I'm connected to different multiple customers. So you can see the green basket as well as the red basket. And let's try to give it more information. I can go to my visualization. I can say, give me my ID and then give me my label. So for customer 12353, the green products are the ones which the customer has already bought, and the red ones are the recommendations. So you can see there is difference in size for the recommendations that is offered. The higher the page rank, it's because like say for example, this particular product 22423, it's high because that's purchased by many customers, in which one of those products has been purchased by this particular customers as well. So this particular product is offered to customer 12353 because the blue customers have purchased these green products as well as these red products, but then customer 12353 has not purchased this particular product. Now, based on the closeness, it associates a page rank. So let's say I right click on this and then I get a page rank of 0.0013. Now, if I try to associate it with the page rank of this particular product, I can see that it's 1.5. So 1.5 is pretty far away from this particular page rank. So the page rank is very high for this product, and that's why it's offered. It's offered as the maximum possibility of customer 12353 purchasing this particular product. What we can also see that you can set highlights. So let's say, for example, one reason why we have different vertices highlighted in different colors and different sizes, it's because we are mentioning this based on the page rank. You interpolate the size of the vertex. You can also give icons to various vertices. You can have conditional formatting done to the edges as well. So based on various conditional formatting, you will be able to get a visual representation of how easy it is to find the hidden insights and the patterns. And that's how basically run a built-in analytics algorithm and then leverage graph as a product to find out like the hidden insights. So in this example, we are looking at a recommendation-based example wherein we use a personalized page rank and then got this information. One last slide for this particular session. How is Oracle Graph different? First is the scalability and performance. It's built in the Oracle Cloud infrastructure. We also have the graph offering in the on-premise environment, and it's been proven and tested by running large-scale data analytics on top of database versions. We basically load millions and billions of transaction-related information or various edge-related information into the in-memory. And then there is a very easy and accurate way of detecting the various patterns by writing simple PGQL queries or by trying to leverage the built-in algorithms. It obviously has a list of built-in algorithms as well as the graph visualization patterns and can be leveraged by various um, roles like the data scientist or the data professional, the data developers, the business analyst, the executive, or from a compliance perspective. And the models can be consumed in multiple ways. You can even write APIs and then generate the graph in a custom web module. I hope that was an interesting session. Thanks for listening to me.